So again, I appreciate the opportunity to get on this webinar and present this information. This is work that myself and Dr. Michelson from Marshall University have led for the Short Span Steel Bridge Alliance. And it's been very exciting work to go from development to implementation in just a short period of 3 years from when we started this concept. And you'll see information later on about some of our members who have now taken this work and other work that they've done to promote this as a commercial system. So it's been quite a successful project. And I think as time goes by, you're going to start to see this as being one of the primary structural forms used in the span ranges for which they're most applicable. And you're going to start to see them being very, very commonly employed. So I'm going to go over, here's the upcoming webinars. There's another one on May 5th. May 12th, May 19th, and May 26th that others of our members are due. And so keep your eye open for those. And again, this has been a good series of webinars to be able to do. And so our other members are presenting on other topics related to this. But what I'm going to talk about today is the background on the experimental work and development efforts that myself and Dr. Michelson at Marshall University did, as well as several demonstration projects that have shown the successful implementation of this. And then I'll talk about the standardization of the design of these. We get a lot of questions about how do you do the design? And basically what we've worked to do is prepare design examples and then standard shapes that are valid for certain span ranges in there. And you'll see that at the end. And then, but again, don't hesitate to chime in the chat and ask questions, and the other members will try and answer those, and I can certainly field some at the end of this. So this is the system that we're talking about. It fundamentally takes all of the properties that you would get in a larger welded tub that was fabricated from multiple plates, but employs them in an economical fashion by taking a standard mill sheet of steel and placing it in a press brake and placing 4 bends in there to be able to get it in this trapezoidal tub girder form. And so we started with this concept of doing this trapezoidal girder with shear studs welded to the top flange and then a cast in place concrete deck on there. But there's a variety of means by which you can employ a deck. You can bring the girders to site in a non-composite fashion and conventionally pour a deck. You'll see actually the first application that we did with the girder was done in that manner. And there's also systems that utilize steel sandwich plate systems. And you'll see a demonstration bridge that we did that utilizes that. So there's a variety of different deck options that you can do with that. So the work really came about as a challenge to the steel industry from the Federal Highway Administration to produce a structural shape that would be economical for modular steel bridge construction in the short span market. And myself and a number of our members got together in Chicago, about 7 years ago now, in a technical working group meeting to discuss various forms that we thought would be successful, and ultimately selected this as the one. And then we initiated at West Virginia University an experimental testing program to be able to assess and evaluate this technology and further develop it into commercial utilization. So we take a standard mill sheet of steel, 84 inches, 96, 120, and we place several constraints on that. We have a top flange width, and we selected that to be 6 inches. So it was wide enough to get 2 shear studs on there. We have a bend radius of 5 times the thickness of the plate so that we are consistent with what will be the AASHTO specifications for that. And we use a conventional trapezoidal tub girder web slope of 1:4, which is what's normally employed in larger welded tubs. So given those constraints, once we then input depth, we can get the maximum moment capacity of the section. Now, we had no idea what we wanted to use at the very beginning of this, so we assumed that they'd at least be able to reach the yield moment in terms of their maximum capacity. And so we varied those depths and all other aspects of the plate geometry, given those other constraints, just fall into place. And we tried to determine what the maximum yield moment we could get so that we could optimize the shape. And so in this plot here, this is a plot with a 96-inch wide plate utilizing various plate thicknesses. And you see that results in about a 26-inch deep plate. So we performed that same design for other common standard plate widths, and that produced for a set of girder depths for each of those. And so, for example, you'll see later on a double girder module that we had looked at early on in the work utilizing 60-inch plate, and you can get a superstructure depth with those of 12 inches for the girder section itself. And I should also mention that if you go to the Short Span Steel Bridge Alliance website, there's a series of reports that are published there that provide all the background information on these. It provides section property information and documents all of the experimental, analytical, and field assessments that we did. So it's quite a big amount of data there. And as you are looking at utilizing these systems, you can certainly reach out to us or to our other member partners who are involved in the commercial production and application and sale of these systems. So once we had done that, we decided that we needed to do some large-scale experimental testing of these, and we selected the plate that was fabricated from an 84-inch wide by 7/16-inch thick plate as the specimen to utilize in our laboratory. And the main reason that one was selected is because we have a maximum applied load capability of 330 kips. And so if we had used a larger girder, then we wouldn't be able to fail that specimen. So you'll see a plot in just a few slides here of the load deflection response for one of these specimens, and we're pushing 315 kips or so on there, which is an awful lot of load. So we took the 84-inch wide, 7/16-inch plate and had those fabricated in tub girder dimensions that you see here, and placed a reinforced concrete deck on there to initiate experimental testing. And we've tested composite sections, non-composite sections, multiple girder modules, fatigue loading. I mean, we've ran the gamut of possible scenarios that you can imagine for testing and evaluating that system, and it proves itself to be very, very robust. So here is a series of pictures that have to do with the experimental testing. You see in the upper left-hand image, that's the production of one of these. And so essentially what one does is take a sheet of steel and place it in a large commercial brake press and basically put 4 bends on it to create the top flange bends, and then turn it over and bend and create web bends in there. And once you have the jigs and everything set up for these, you can produce the girders in less than 45 minutes in a typical setting. And I should note that there are a number of commercial press brakes around the country, and most of them are limited to a maximum width of 60 feet. So that sort of 60 feet or less tends to hit the spot for where these are most successfully employed, but they're applicable to span ranges that exceed that and go up to about 100 feet for certain plate configurations. And so one could just use additional splice in there if you wanted to use the girders in lengths that exceeded the available press brake width there. So you see that being formed in that upper left hand image, and then the upper right hand image there. You see it in our major units testing lab here at West Virginia University. And it's basically just now set up there on those load cells in a simply supported fashion. And then we begin forming the deck. And what we've done in the lab to form the deck was to just simply use sacrificial plywood formwork. And in a latter application that you're going to see that was done here in West Virginia, in a challenging site, the material supplier elected to use this same forming fashion as well, and it tended to be quite successful. So you could use stay-in-place metal formwork or this sacrificial plywood formwork, whatever was in project. But you see, we've just formed that up in the lab, and then we poured a deck on there and allowed that deck to cure for at least 28 days. Then we've instrumented the girder. Here you see a series of deflection gauges, those LVDTs in the upper left-hand image. You see the girder sitting on load cells at the end of it to be able to record their reactions. And you see a series of strain gauges that have been applied to the girder both on the inside and outside of the webs and bottom flanges there. And then in that right-hand image, what you see is the 330 kip actuator that can apply the load at the midspan of that. So we're just testing that in bending in this particular test to evaluate maximum capacity and obvious stresses and strains and deflections in the girder and those types of things. Now, here's kind of a neat shot, because that left-hand image is the girder when it's reached its maximum moment capacity. And what you see in there is exceptionally small deflection. So once these are closed, once you have a closed tub girder shape, the moment of inertia is just orders of magnitude larger than you would get compared to a conventional I shape. So they're very, very stiff systems. And you see the girder at the end in the upper right, and then that lower right-hand image, what you see is the method of your girder. And this isn't strictly how you would see just a tub girder fail. This is how you would see a composite eye girder fail. You would normally see the ultimate moment capacity being controlled by ductility. You would start to see the concrete deck crack. You start to lose moment of inertia, and you start to get larger deflections in there. So this fails the same way as a conventional eye girder would fail, through the ductility of the cracking in that concrete deck. Now, These, as you can see, these are big tests to set up and conduct, and they take a long time to be able to perform. And so in order to research other aspects of these, we want to be able to develop modeling that's successfully capable of capturing their behavior. So we use a commercially available finite element software called Abacus, and we simply model the deck and the girder using shell elements. And you can see, and that you see a picture of that model in the lower left-hand corner there. And what you see in the plot in the right-hand image is the FEA model compared against two similar experimental tests. And I would say for all intents and purposes, those are just essentially dead on. And so you see that maximum moment there of about just over 300 kips. And we're modeling that accurately. So what we did is once we successfully can duplicate the results of the experimental study, we wanted to look at analytically capacity plot of all kinds of varying scenarios. So we took a variety of the different girders that we had seen before that came out of that depth versus MY plot. We looked at using grade 50, grade 70 steel, and a variety of different deck options. So we have this matrix of about 900 girders that we then modeled analytically using that same finite element program that captured their behavior. And what you see there is a plot of the AASHTO moment capacity compared to that blue cloud of data. That blue cloud of data is essentially the results from all of those individual girder analysis permutations. And that I'm going to hone you in on the moment capacity compared to AASHTO. You see that AASHTO is conservative in its prediction of capacity. And if you had a plot of I-girder ductility checks like this, you'd get that same conservative behavior there. So AASHTO conservatively predicts the maximum moment capacity of the section. And so we oftentimes get questions, well, how do you check the capacity? And we just use AASHTO 611 for tubs, and it's successful. And as far as distribution factors go, there's a minor detail that has to do with the center spacing of web, this adjacent center spacing of web at the top flange in a tub, that these don't meet because the module is wider than that. But it proves it out when you do a series of analyses that those AASHTO distribution factors are conservative as well. So if you simply use the AASHTO distribution factor along with 611, it adequately predicts the strength of these sections. And then we also have design examples available that walk through that. But again, we're not suggesting that each time you would employ this system, it would be a one-off design. We want to move as an industry towards total standardization. And you'll see that at the end of this presentation, what we've done with that. So we also, in order to evaluate the stability of thin-walled open shape, we tested non-composite sections in there. And you see this global lateral torsional buckling of the system, which you would expect to see in there. And when we go back to some older work that was done in determining that buckling capacity, our experimental results gave us 95 kips, and the theoretical solution gives you about 93 kips. So again, we're pretty good there, and we've moved into looking at some additional stability criteria for these as far as bracing the section if you were going to do it in the means of a conventional cast in place system, which can be done. We also wanted to look at the performance of joining these with ultra high performance concrete. And so we did a 2-girder system in there, where what we wanted to do is evaluate the efficiency of that joint over the predicted lifespan of the bridge and determine how successful that would be. And we built on work that was done by Dr. Ben Graybeal at Turner Fairbanks, where he had looked at a whole host of different edge configurations and mixes. And we basically took the one that was found by Dr. Graybeal to be the most successful and employed it in this system to assess its capabilities. So here you see 2 girders in there, and they're separated in that upper right-hand image to be able to pour both of those decks. So we poured those, and in order to do this, you put a retarding agent on the edge of that so that you don't hydrate all of the cement at the edge, so that you can get this roughened surface in there. So here you see the module with the rebar sticking out of it. And you can just take a pressure washer basically and spray that non-hydrated cement off of the edge. But in our lab, we can't do that because we can't run a pressure washer inside the lab. So one of the graduate students took a wire brush and just wire ground that edge. But you see that sort of roughened surface that's produced there in that lower right-hand image as a result of having that agent placed in the forming. Then here, once those girders are set up, we move them close together, so you're able to develop that joint over just a 6-inch spacing between the girders. And here you see the forming that's going on there. And I have to give a shout out to the University of Virginia, because what you see in that middle upper image is University of Virginia's brand new pan mixer that they loaned us to be able to do this. They had just bought it for some research they were doing. They hadn't started that research and let us use their mixer. So we had it shipped over to us. Had a company that produces the UHPC come to perform quality control of the mix and place that in there. People often ask, what's it like? Is it really fluidy? It's more like thick molasses as it flows, and it becomes, and then you work it into that joint, and you tend to typically pour it just slightly high and then grind that off. So what you see there in the middle lower image is one of the graduate students grinding that joint down to have a smooth surface. And then the application that was just completed in West Virginia, they had a grinder come out and grind the surface of the bridge, and you'll see an image of that. So what we did was we determined what load applied at midspan would produce the strength 1 moment. We determined what load would produce the service 2 moment, and we determined what load applied at midspan would produce the fatigue moment in there. We predicted the rural fatigue life for this, and it came out to be about 2.7 million cycles. So what we did was apply that fatigue load over a range of about 100,000 cycles. We would stop that, and then we would apply the load up to the service 2 load, incrementing it in tenths of that load, and evaluated the stress and strains in there. So what you would suspect, if the UHPC joint was not working, then over the life of that bridge, you would start to shift more of that load away from that unloaded girder into the loaded girder. And we found that not to be the case. So what that means is that joint worked very well over the predicted life of that bridge. And there's been a number of applications utilizing that now very successfully in there. And this is a plot that sort of demonstrates that. Now, what I'll key you in on is the right-hand plot. What you see is the loaded girder and unloaded girder, and the applied load versus strain in there over these series of increments of loading, 500,000, a million, et cetera, all the way up to 2.8 million. And you see essentially no shift in the load pattern, therefore indicating that that UHPC joint was successful over the expected life of the bridge. This is showing a plot of taking that up to failure. And you see here the predicted strength one load at midspan that would produce the strength one moment was 126.5 kips. And you see it behaving linearly up to there. And it continues to exceed that load that would produce the strength one moment. Ultimately, because we chose to use a load pattern that was simulating the AASHTO wheel load size, then this test failed through punching shear through the deck in there. We then, after the first 3 years of development and testing of this, we were able to put the first bridge in Buchanan County, Iowa. And Brian Karl E is the county engineer there. And he applied for and received a grant to assist in the construction of that. And here you see the image of that bridge and the ribbon cutting that was done. And we then went and performed experimental testing on that. So these are the companies involved in the production of the Amish Sawmill Bridge. You see the contractor, the fabricator, the press brake former, and the galvanizer. They used a GRS abutment in there, and you can see that image of that wall, that GRS wall that's there for the abutments. And we went out and used removable test system that we have, and it uses these wireless sensors that are screwed on to tabs that are using an adhesive to place on the bridge. So that left-hand image shows you what one of the strain gauges look like. And then it has a wire that comes out a short distance to the wireless node that's shown in the middle. And that then sends the signal to this to the data acquisition system. And so what we did was instrument the bottom flanges on there and webs of 2 of the girders. And then we took a loaded vehicle out and ran it both transversely and longitudinally along a number of lines that would maximize the load in a 1-lane loaded or 2-lane loaded position to each of the girders. And then we looked at the distribution factors to those. And here you see those distribution factors being plotted for each of those girders. And what we don't have on this plot is the distribution factor that you would see from AASHTO, but what you would see is that it would be conservative related to this. So again, just simply straight up designing these as tubs from AASHTO is fine, but we provide standards, so you would not be, again, designing these as one-off each time. We've done several other demonstration projects. Here's one in Muskingum County, Ohio, and this bridge actually won a National Steel Bridge Alliance Technology Innovation Award. This is combining the tubs with a sandwich plate system. And in this particular bridge, the entire bridge came out as two girder modules on one truck. And the contractor did the main erection of the bridge in under 20 minutes. They basically picked one module up, set it on the bearings, and picked another module up and bolted them together. And most superstructure completed in less than 20 minutes. So when we talk about accelerated construction, I don't think we can get much quicker than that in there. We similarly perform experimental testing on that. Here you see a couple of images of them picking those modules up and placing those. We again went out using the same removable data acquisition system and employed that same testing that we had done before on it. Here you see what the bridge looks like once those girders were there. And here you see in the right-hand image the railing being bolted onto those posts that are on the edge of that, and the forming of the approach slabs that are there. These are the companies involved in the production of the Muskingum County Bridge. So you see the bridge contractor, the bridge fabricator, and SPS Americas was the one that supplied the steel deck on there, and AZZ did the galvanizing of it. Again, we went out and used that same data acquisition system to conduct similar experimental testing on it. Here's a bridge that was just recently completed in West Virginia DOH District 2. And what I'd like to say about this bridge is we had some challenging site constraints on there. You'll see some images in just a couple of slides where this site has both super elevation and skew. And so that had to be incorporated into the forming of the deck and the girders. And it worked really, really successfully. So what we like to say about this project is it shows that if it worked on this site, it'll work on any site, because it'd be hard to get more challenging site conditions than we had on this. And you can see in what they're doing is using that same sort of approach with the sacrificial plywood formwork to be able to get that cross slope on there. And you can see the difference in the shear stud heights on either side of that. And you can see the skew from that bearing plate that's in there as well. So again, quite a bit of complicated site geometry, and they were able to work with this system very successfully. Here's forming of the deck. They used reusable formwork on the outside of it. You can again see that skew in the right-hand image on there. And you see that rebar coming out from the deck forms there, where it's going to be employed in that UHPC joint. So this was a very successful application of the girders. Here is them placing the deck and then finishing that. And then you'll see a couple of images here of that bridge being erected there. So in this application, the bearing seats were poured integral with the girders, and you see that module being brought out to the site. There were 5 girders, and they came out as a single girder on 5 different trucks, and then they simply lined the trucks up and took one girder off and placed it on, and that truck would move out of the way and they would bring the next truck in. So you see that first module being placed on the abutment back walls there. And here's a couple more images that sort of demonstrate to you the site. So you can see the skew on the site there, and that truck being brought around through a temporary bridge. It was kind of cool. The DOH brought out a drone to do some aerial recording of this, and that video is really pretty neat to be able to see. You see on the edge of this where one of the modules is next to another one, you see that exposed aggregate detail that's on there that was discussed in the laboratory work to be able to adhere the UHPC to it. And here's them pouring the UHPC into the joints there. The contractor was able to successfully do that. And then here you see them using a diamond grinder on there to be able to get it. So we have one other demonstration project that's going on in District 4, and that should be going in the fall. And then a number of our members who are involved in this have placed numerous other ones of these bridges very successfully. It's a super economical and super robust system to be able to use. And I would suggest whenever you have need for bridges in the span range, that this is something to definitely be considered. These are the people who are involved in that West Virginia bridge. You see the contractor, the steel supplier and fabricator, and then the galvanizer was VNS Galvanizing. Now, one of the things that I've alluded to several times is you don't need to design these every time. We want to move as an industry not only in the tubs, but with I-shaped girders, plate girders, and wide flange sections into the notion of standardization. And so we'll have 3 different span ranges in which a different section is recommended to be utilized in there. And what we did was simply vary the span range from 20 to 140 feet in 5-foot increments and look at all of the applicable AASHTO limit states for those in order to try and determine the span range of applicability for those different plate widths that were shown early on in there. And so that results in a series of plots that look like this. This is just for the 96 by a half. And so what you see is demand versus capacity. And wherever the demand in blue exceeds the capacity, that would be the maximum span range that it was applicable for that given limit state. So, for example, you look at shears. There are 2 webs, so you never exceed shear capacity. They're just buku strong for shear. You see in the upper left the plot of capacity versus demand for strength 1 moments, and you see that demand passing the capacity at just over 60 feet, around 63 feet. So that would suggest that utilizing the distribution factors that we utilized and that plate size, that would be applicable for spans up to 60 feet. So the shortest one of those would be the maximum span, right? Wherever you violated a limit state first would be the maximum span you could utilize in there. So here you see for all those different plates that we had discussed early on, you see a series of plate thicknesses. And you see the AASHTO versus a proposed limit state that we had worked on early on. Because AASHTO worked so well, we've not worked to advance that. So that's what that red and blue are, as a limit state that we had developed from that cloud of data. But I'd key in on just the AASHTO plot for each of those. And so you see for those different plate thicknesses, and plate widths, maximum span ranges of applicability. In all but one case, they were controlled by strength. There was one, the 84-inch wide 7/16 inch plate was controlled by live load deflection, but that was the only one in there. We then turned to work that was produced by Chris Garrell and others at NSBA that looked at plate size availability. And you see that for the 72, 96-inch plate, that for a half inch, it's available up to 972 inches. So therefore, and most mills produce a half-inch plate. So it's virtually available every day. People ask about steel availability, and when you're talking about standard sizes and thicknesses, they're virtually always available. We increased the thickness from a half inch to 5/8 for the 120-inch wide plate, not because it was necessary from a structural capacity standpoint, but from a material availability standpoint. You see that the 120-inch wide plate in half inch is only available up to 750 inches. And so by moving to 5/8, it gets it out to 972 inches. So what you see then is here are those ranges of applicability for the different plate sizes. And we produced a series of drawings that are going to go into our online software called eSpan. If you're not familiar with that, I believe Dr. Barker would have talked about that in one of the earlier presentations. But it's an online design or an online standardized tool that we have available. And this is going into an update in that. And you see these different standard plate sizes. So if you have a design that's less than 40 feet, you'd simply use this plate. You wouldn't, if it was 37 versus 36 feet, you wouldn't go in and design that each time and try and resize your tub accordingly. You'd simply select the tub from a series of standards based on what your span range was. And standardization just makes sense for just a whole host of reasons. And so here's a common range is the 96-inch plate, and it's applicable from 40 to 60 feet. So again, if you have a 47-foot girder, you're not going to come in and try and resize the tub and design specifically for that. You're just going to take the tub girder design that was standardized for the 60-foot section and utilize it for that. So in each of these three sheets, we have recommended deck detailing. We have abutment detailing that's similar to what you saw in that bridge that was done in District 2. And we also then have a tub that at a 120-inch wide plate that's applicable from 60 to 80 feet. Again, you would find that most common press brakes were not longer than 60 feet. So you would need to use a splice in there, and you would just use AASHTO splice design and design it as though it's a common bolted field splice in there. Here's a number of our members who are commercially involved in galvanizing production of the girder systems themselves, and have also independently put quite a number of similar girders out there. So I reference you to them for further information on there, or don't hesitate if you're evaluating this system to work through us through the Short Span Steel Bridge Alliance Bridge Technology Center, and we can help point you in the right direction with technical inquiries and help you assess this system for your projects.